Okay, so what we've said so far is that the job of CSPF is to come up with an explicit route object. It will then pass that explicit route object to RSVP, and RSVP will then build our path for us. So what happens then if we put all of our constraints in and to the algorithm, and it comes up with more than one possible path that meet all of our constraints? Well, it has to have some mechanism for making a decision. So that's where the tie-breaking functionality comes in. So let's take a look at tie-breaking. So how do we make a decision? Okay, so the following terms are formulas that are used in our tie-breaking formula. We have this thing called reservable bandwidth, which is the link bandwidth times a link subscription factor. We have available bandwidth, so reservable bandwidth minus the bandwidth that's already been allocated to other LSPs. The available bandwidth ratio is the ratio of the available bandwidth to the reservable bandwidth. In other words, it's really the percentage of available reservable bandwidth, or sorry, the percentage of available bandwidth that is left. So if you take a look at how much bandwidth we started with, how much is left? Is there 50% left? Is there 10% left? That's kind of the ratio. Then there's the minimum available bandwidth ratio for a path, so the smallest available bandwidth ratio of the links that comprise a path. Okay, so we've got some things that our tie-breaking rules are going to consider. It's going to consider these things. So let's take a look at our tie-breaking options. So what we're talking about here is that we put all of our constraints in, and we've been able to meet our bandwidth requirements, our hop requirements, our priority requirements, our path requirements. We've met everything, and we've come up with two paths that have got the same amount of hops with all of our requirements, and now we have to make a decision as to which one of those we choose. So here are the possible ways of resolving that dilemma. There is random. In other words, just toss a coin, pick one, it doesn't matter. We'll just pick one. That's the default. It'll just randomly choose one path. And it kind of tends to balance the total number of LSPs over all the available paths. The other possibility is we could set the tie-breaking rules to be least filled. So this is a user configurable option. In this case, it finds the path with the largest minimum available bandwidth ratio. In other words, if we've got one path that is 80% filled already, and 20% left, another path that's only 50% filled, so it's got 50% left, it will choose the path that has got the 50% available bandwidth, because that is the least filled path. Then there's the most filled path. With the most filled, it would have chosen the path that is already 80% filled and has only got 20% left. So why would you choose that? Well, maybe our goal is to fill up all the paths completely and then allow other paths, which are not filled, which then have bandwidth available, to be populated with new paths. So maybe that's our goal. With the least filled, what we're trying to do is just kind of balance the load over our entire topology. So we have these options, with random being the default. So we can change that in the edit protocols, MPLS, labels with path name hierarchies. We're going to change the default behavior. Okay, let's just take a look at this tie-break mechanism. Remember, this only happens if we fulfill all of our requirements. We come up with more than one path. They've both got the same hops, both got everything equal, and now we have to make a decision. So if we have said that we would like to use the least filled method, so we're going to then build our path, build our new path across the links that are least filled. Well, the first thing is that they must have the same number of hops. So it's going to choose the path with the least number of hops. So if we look at the possibilities here between ingress and egress, we find that the two paths with one hop are the top path and the bottom path. The paths in the middle have got two hops. So it's never going to choose those middle paths because they've got more hops. So that's one of the tie-breaking requirements. It will always choose the path with the least hops. But we've got two paths with the same number of hops. So the question is, if we're using least filled, which path will a new LSP with a 12 meg bandwidth request take? So we have got, so we're saying, first of all the paths are past Ethernet, so they're all 100 meg paths. This one has got 65 meg available, it's the top path. Our bottom path has got 15 meg available. Okay, so basically you could say the top path has got 65% of its total bandwidth available. So 65% of its reservable bandwidth is available. The bottom path, we've only got 15% of its reservable bandwidth available. Both paths have enough bandwidth to satisfy our 12 meg requirement, but if we are going to use the least filled option, or the top path is least filled because it has 65% of its bandwidth available. So in this tie-break rule, the top path is going to be the one that is chosen. Okay, what about most filled? Well, then of course it's going to take the bottom path with the most filled option because the bottom path has only got 15% left. So it is the most filled path. Okay, so let's just take a look at that scenario with those tie-break rules. What about this scenario here? All the links are allowing a 100% subscription factor. That means that we are making all the possible bandwidth available for MPLS, not reserving any bandwidth for anything else. If we say that the top and bottom links are gigabit Ethernet links, top and bottom links are gigabit Ethernet links, the middle links are fast Ethernet links, what will happen now? So we're using least filled. Well, the issue is that the middle links have got more hops in them, so they're not going to be used. That's sort of the issue there. The top and bottom links have got, what are we doing here? Top and bottom links are gigabit Ethernets. All paths are equal metrics. So which path will it take? Least filled. So that's going to be the 430. Available links. So we've got 430 meg on the bottom one, 500 meg on the top one. That is the available. Shows reservable bandwidth. Next thing shows reserve bandwidth. So that's the reserve bandwidth. So the bottom half actually got more bandwidth available, hasn't it? Yes, it does. Okay. So let's look at this one here. Top links are fast Ethernet, bottom links are gigabit Ethernet. Each link shows the reserve bandwidth. So this is the bandwidth that is used already. We information on these links. So we have got 5 meg is reserved on the top link. The bottom link, we got 200 meg is reserved on the bottom links. Bottom links are gigabit Ethernet. So here's the interesting thing. The bottom links, we've got 200 meg reserved, we've got 80%, so therefore 20% reserved, 80% is available. Of the top links, we've got 5 meg reserved, therefore 95% is available. Using the least filled method, it will actually take the top link over the bottom link. So even though the bottom link has got more total bandwidth available, it has only got 80% left, whereas the top link has got 95% left. So it's based on the ratio, not on the actual amount of bandwidth that is left. So that's how our tie break works. Okay, let's get into these administrative groups here. So what we have available to us is a total of 32 named groups, 0 through to 31. They're carried as a 32-bit value in the IGP updates, and the groups are assigned to interfaces. They are referred to as color or link affinity. So usually it's quite common for us to use a color to describe the links that we're setting up. So the process is that we will say, okay, well the link here, so we've got a gold link, we might have a bronze link here, so we've got a silver link over here. So what we're doing is we're going onto the router, onto the interface of the router, and we are defining this link affinity rule, which are really called administrative groups. So this is administrative groups are defined on the links on the router. Now, what you have to do to make this work is that if I go onto this router over here at San Francisco and I say a particular link, say is a gold link, then I have to go onto the other end of that link, and on the router at the other end, I have to define it as a gold link on that router as well. So in setting these things up, it is important that the configuration matches both ends. It's the same at both ends of that link, otherwise we're going to have chaos. Okay, so we can go ahead and set up these what are called administrative groups or link affinities. Often or mostly we use colors to define those. So colors are advertised on a per link basis using the IGP. So we use a hexadecimal number to advertise those. They're assigned on the router, usually set up as bronze, silver, gold, etc. Okay, so here's an example. So here's our admin groups. We're on our radar, on R1, we're defining our admin groups. Gold is 1, silver is 2, bronze is 3, management 30, internal is 31. We then go on to the interface itself under the admin group hierarchy, and we're going to say this interface is gold and it's management. So an interface can belong to more than one group. Going on to our next interface, and we're saying this one is silver, and then the next one, this one is gold, next one, this one is gold. Okay, so we're assigning these administrative groups onto our links. Why are we doing this? Well, we're going to be able to feed this information into our CSPF algorithm when we're building paths. So CSPF can factor the include any or include all and exclude constraints into a path calculation. So here's an example here. We have got a lattice switch path which says to Miami. The egress router is 1.1.1.1. We have a primary path here which is called use Fargo, admin group. And what we're saying with our admin group is we can say include any gold and silver, include any premium and customer, and exclude any bronze or iron. So we can go ahead and, as part of our constraints, define these administrative groups, which have to be included or excluded in our path. So we can say the path can take any gold or silver, or it has to take all, or it has to take none. So there are our three possibilities: any, all, or none, basically exclude. And we can also then put this loose hop in our path as well. So this is just the constraints that we have put in so far. Okay, so if we do a show MPLS interface command, we will see the administrative groups that are assigned to particular interfaces. Here we've got gold assigned to both of those interfaces. And let's take a look at using these administrative groups then to choose the best path. Okay, so the numbers represent the IGP metrics. So let's choose the IGP's best path from A to I. So here we are with A. Our destination is I. What's the other side of our topology here? Using the IGP, what is the best path? So what we're going to do, we're going to add up all the metrics on the way to I, and whichever path has got the lowest number, that's going to be the IGP's path. Okay, so let's just take an example. What if we took the top? We went from A to B, that's 1. B to G, that's 5, so we've got 6, and then over to I, that's another 1, so that's going to make 7. So going across the top, we have a total of 7. Or if you go from A to D, that's a total of 2, 3 up to E, 4 up to G, and then 5 across to I. So that would be a better path, because we've got a total metric of 5 going A, D, E, G, and we have a total metric of 7 going A, B, G, and I. Are there any other paths that may be better for us? What if we went from A to D? That's 2, that's 4 across to H. No, we've still struck out there with 7 up to I, so we haven't beat the A, D, E, G, I path yet, have we? 2, 3. So what have we got? We're going 2, we're going 3, we're going 5, or we're going 6. So we've got 6. Count, we are 6 up to I. 6. So A, D, E, G, I is 6. And I can't spot a better path than that. We go A to B, 1, 4 down to E, 5, 6, 7. So far, I think that the A, D, E, G, I looks to be the best path, and there it is. That is our best path. Okay. So that's the IGP's best metric. I'm getting to A to I. Okay. Now, what would happen if we said build a path from A to I, and what we want to do with our primary path, we're going to use administrative groups, and we're going to include any gold, and we're going to we can include any silver, any gold and any silver. So here we are with I. Okay, let's evaluate our constraints. Can we go up to B? No, because that's not gold or silver. That's labelled as an admin link. Can we go across to D? No, that's a copper link. It's not gold or silver. Can we go down to C? Yes, that's gold. Okay, good. Can we go, where can we go from there? Well, from there, we can go from C across to F. That is gold. All right, from F, can we go across to H? No, that's F. Admin, we can go up to G though, because that's silver. And we can go from G to I because that's gold. So our new path, based on our constraints, is A, C, F, G, I. Okay, based on those constraints. And there's our path. Okay, so what we're able to do while using these constraints is to calculate a path which is different to our interior gateway protocol's best path. Okay, so we're using only the gold or silver links. All right, let's take a look at the scenario here. Choose a path from A to I according to primary path. We want to include any copper and bronze, but we want to exclude admin. That means we cannot take any path that is an admin path. So basically, we've got to go copper or bronze. So really, I'm going from A across to D because that is copper. I could go up to E, or I could go across to H because either of those paths would map because there's a copper up to E and there's a bronze over to H. Okay, so either of those paths are fine. So what is going to be the best path based on the metric according to that? So we've got a metric of 4 across the going up through E, G, and we've got a metric of, what have we got there, 5 going across to H. So we're going to take the best metric, which will be the one up through E, and then G, and then across to I. Let's take a look at that path there. And yep, that's the path. Actually, we didn't go up. No, we didn't go across to I because we couldn't go across that link. We had to go down the bronze and then up to the copper. Okay. I had to exclude the admin link, so we couldn't go across the admin link either. Notice that that path from D across to H is bronze and admin. So it's actually got 2 colours on that link. So even though we could have included the bronze, we had to exclude the admin. So we could have used that path. We had to exclude on that admin. So what we had is we're allowed to go to copper. We're allowed to go up to the next copper up to E. We went up to G. We couldn't use the gold, but we could use the bronze down to H and the copper up to I. So by putting these constraints in and using our link affinities, we actually then allow the CFPF algorithm to calculate a path that suits the requirements that we've given it. Okay, choose a path from A to H using include any copper and bronze, exclude any admin. So we're going from A to H. There's our H222. So there we are. Include copper. We can go to D. From D, we can't go to H because the link between D to H includes admin. You have to exclude that. So we can go up to E. From E, we can go up to G. And then from G, we can go down to H. And there's that path there. Actually, it went the other way, didn't it? Because it had a better metric. Yeah. Went to I. Going to I had a better metric. Yeah, that makes sense. Okay. Choose the path from A to H using. This one does include all. So we have to use all the gold and all the silver links going from A to H. So can we use all the gold? So we go down to 3, that's gold. We go from C to F, that was a gold. We're going from F to G, we use a silver. Our goal is to get to H. There is no gold or silver links there to get us to H. You can go there. Can we go there? From G, gold or silver. So it says include all gold and silver. So we're at G and we've got to get to H.
There is no path.
What happens? No path, exactly. You can't build that path. All right, so it's possible to put constraints in that are actually impossible to satisfy. There is no path. All right, so let's take a look at this here. Will CSPF prune length C to D when choosing the path from A to H using this constraint? The constraint is exclude admin. Will it prune the length from C to D? Let's have a look at C to D. There's C, there's D. We're excluding admin. No, I don't see admin on the link from C to D. So, no. It won't prune that path. Not based on that anyway. Okay, so what have we covered so far? With our constraint shortest path first, we have described the path selection process of RSVP single data Cs without the use of CSPF, and then we've described the ITP extensions needed to build and maintain our traffic engineering database. We've explained how the CSPF algorithm selects the best path based on provided constraints, and we've looked at how administrator groups can be used to influence the path selection. So let's look at some questions. Describe how ISIS and OSPF support traffic engineering extensions that build the TED. Okay, how does ISIS support that? Yes, it does, and it has been extended to flood these things called TLV tuples. Okay, so ISIS uses TLV tuples. OSPF uses type 10 opaque LSAs to flood that information. Okay, there's 3 user inputs to the CSPF algorithm. So what types of constraints can you give it? Just name one. What's a constraint? I need this. What can we say? What can we tell it? I need a certain amount of bandwidth. That would be a constraint. Must have a certain amount of bandwidth. What's another thing we can tell it? Yeah, we can say it must go through this path. So we can put strict or loose hops in paths into it. What else about the hop can we say? We can specify a maximum number of hops that we are going to allow in our path. So a maximum hop count. What else can we tell it? Yeah, administrative groups. So we can say links. I want red links, blue links, bronze links. I can put that in as well. Okay, so yeah, all those things. What is the default CSPF tie-breaking algorithm? What's the default tie-break? The 3 possibilities. There's random, there's least fill, and there's most fill. What is the default? The default is random. So if we don't tell it anything, it will be random. Describe how administrative groups can be used to control path selection. So what are our possibilities with administrative groups? There is include any, include all, and exclude. So they are the 3 things we can do with those groups, and we can define those as constraints. All right, guys, very good. What we're going to do next is we are going to be doing labs. We'll actually do all the labs on our constraint shortest path first. And we'll just sort of pick up where we left off from last week, do a bit of a recap on where we were at, and then we'll go on and implement our CSPF. And that'll be after lunch, okay? So we'll come back after lunch, and that's what we're going to do.